Good afternoon, everyone. My name is Daniel Guaman, and I come from the Computer Science Department of Universidad Técnica Particular de Loja from Ecuador. It's a pleasure for me to participate in the 37th Symposium on Applied Computing. And I'm going to present our work, which title is Estimating the Energy Consumption of Software Components from Size, Complexity, and Code Smell Metrics. The contents of my presentation are the following: the introduction, the problem, the objectives, our proposal, complexity, and code smell energy model, the conclusions, and future work. In these days, the software system contains complex software structures as a consequence of continuous change in the software at code or architecture level, inclusion of new rules and business requirements, limited architectural documentation, the need of paying more attention to the technological improvement. These four consequences, together with a fast time to market, generate low quality in the software, affecting to some quality attributes, maintainability, performance, and the topic that this work is focused, software sustainability. Now, the challenge is to build software more sustainable that meets the future needs, but reduce the carbon footprint and the energy consumption. This work is focused on the environmental dimension, and the objective is to identify and collect metrics based on green software characteristics, so that after an analysis and evaluation, define a model so the software is greener, more sustainable. One aspect to keep in mind that the software engineer design a solution and write code don't take into account features, standard, or reference framework that allow the estimation or optimization of hardware resources. Although software systems don't consume power directly, they affect hardware utilization, leading to indirect power consumption. Models focused in green and sustainable software as GreenSoft suggest the inclusion of sustainability criteria and tools to obtain and evaluate metrics that contribute to the dimension of sustainability. There are some works that define metrics that allow us to estimate software consumption from the code. And there are works that demonstrate that the structure of an object-oriented application influence in this power consumption. This work is based on this premise, and it wants to validate that the application quality is related to its power consumption. This work needs to execute software application to obtain metrics and to estimate energy consumption. However, this execution implies an additional power consumption. But it's important to take into account that in agile process, this power consumption derived from the estimation measurements is never higher, because applications have to be measured many times during agile short interactions. As a result, it's necessary to avoid the rebound effects of estimating power consumption. A solution to this problem is to use model for power consumption estimation without the need of executing a software application and only using software quality metrics. This work is a first step to address this solution. To that end, the following question has to be addressed. What kind of quality metrics can be used to estimate energy consumption at architectural or code level? Could we provide a guide to the engineers to estimate the energy consumption on an application only based on quality metrics? Could we estimate energy consumption without running the software application? Our model is called Complexity and Code Smell Energy Model. It takes as a reference the generic energy cost metric proposed by CEO, who presents a framework that facilitates early estimation of energy consumption induced by an architectural style in a distributed system. And we focus on the estimation. In this work, we propose a model to estimate energy consumption of an architectural component without the need to execute a software application. The component energy cost estimates the power consumption of components and their interactions. The main objective of our complexity in code smell energy model is to estimate the energy consumption generated by a software components in terms of size, maintainability, and complexity, without the need to execute the application. To address this objective, we define two hypotheses. The first, the energy cost of all the components of an architecture can be accurately estimated from their size, complexity, and maintainability. And the second, complexity and maintainability cannot be neglected in the energy cost estimation because both are significant. And we define our multiple linear regression model taking into account the variables size, lines of code, cyclomatic complexity, code smells, and duplicated lines. The phase, tasks, and inputs that are part of our model can be formalized in STEM. The main phase of our model are building, profiling, analysis, and construction. These phases are supported by tools, algorithms, and software models. Let's start with the building phase. The building phase consists of two tasks: find and select software application and compile and build the application resulting from the selection. After applying inclusion and exclusion criteria, 42 applications were selected to be part of the trained dataset. The resulting data is shown in the table. The profiling phase is composed by two tasks: static analysis and dynamic analysis supported by tools. In this phase, SonarQube, as a tool of static analysis, extracts and calculates the values of the size, complexity, and maintainability metrics of the selected application. In the dynamic analysis, Joule-Meter measures the energy consumption of application during their execution. The analysis phase consists of two tasks: data analysis and data normalization. For this, we use RStudio as a tool. For data analysis, it is required to clean and prepare the data that will be processed and trained by the multiple linear regression model using RStudio tool. For data normalization, a logarithmic transformation was applied on the independent and dependent variables. This method is the most used in the data normalization when there are skewed distributions. The final phase is the construction of the model. To construct the model, we applied the least squares method. After training the model, it was possible to conclude the model has not a multicollinearity problem. And the hypothesis 2 was validated because it was demonstrated that the size, complexity, and maintainability are significant predictors for estimating energy, and they cannot be depreciated. However, it is possible to observe that duplicate lines are not significant. In order to ensure this evidence that we can depreciate the duplicate lines, we applied the strategy stepwise by applying the square methods to the different combination of our model by eliminating one or multiple variables from the initial model, determine the best results. This evidence was confirmed, and we removed the duplicated lines, obtaining the final model that is shown in the slide. But it's important to know that the result obtained is normalized by the logarithmic transformation, and therefore to obtain the estimation value has been applied the inverse function of the logarithm to the model. To validate the final model, we have selected and downloaded from GitHub 8 applications with size, XSS, and that have complex connectors in the architecture, and we extract the values of quality and energy metrics of each application. To measure the model performance and precision of the prediction, we use the root mean square error. It provides a value of 0.78 for the prediction of the 8 applications. We can appreciate in the figure the difference between Joule-Meter and our model, and we can conclude that it is an acceptable prediction for guiding engineers in their sustainability decision without executing their application. So we can conclude that the results exposed in this work are the basis to investigate whether energy consumption is correlated with more than one quality attributes. The model is acceptable for the energy estimation and application. The adoption of the proposed model is possible during the construction and maintenance decision-making of X and S application without being executed. As a future work, we aim to build a model that also considers other types and size of application and taking into account the key role of complex connectors in the software power consumption. Thank you for your attention. If you have any question, it will be a pleasure to answer them.